All right, let's get into it. Have you ever just stopped and wondered what everything is actually made of? Like, how does it all work? Now, forget all those complicated formulas you might be thinking of. Chemistry isn't some scary, impossible subject. Honestly, it's the universe's rule book. It governs everything from the air you're breathing to the very screen you're looking at right now. So yeah, let's dive in.
You know, I absolutely love this quote from Roald Hoffmann, a Nobel laureate. He just nails it. Chemistry isn't about memorizing 100 elements on a chart. No, it's a creative science. It's about knowing the building blocks and then using the rules to transform them, to build an almost infinite number of new and incredible things.
And this whole idea of understanding the stuff around us, well, it's an ancient quest. We are definitely not the first people to ask these questions. Way back around 600 BCE in ancient India, a thinker named Acharya Kundan came up with a theory of paramanu, these tiny, indivisible particles. Does that sound familiar? It should. It's the same basic idea that John Dalton would propose with his atomic theory more than 2,000 years later.
Okay, so if we're going to understand the rulebook, we have to start with the players on the field. What are these universal building blocks made of? Well, it all boils down to one simple thing: matter.
So what in the world is matter? It's simple, really. It's all the stuff, the physical things in the universe. It's the air you're breathing, the water you drink, the device you're watching this on. If it has mass and takes up space, guess what? It's matter.
And this stuff usually shows up in one of three states. The easiest way to think about it is with water. As a solid, ice. Its tiny particles are locked into place, super orderly. That's why it has a definite shape and volume. As a liquid, those particles can now slide past each other, so it takes the shape of whatever you pour it into. And as a gas, steam, those particles are just going wild, flying all over the place to fill any container they're in.
Now, beyond just solid, liquid, or gas, chemists have this really neat way of organizing, well, everything. Think of it like a giant flowchart for the universe. So you start with matter. First question, is it a pure substance or is it a mixture? If it's pure, is it an element, like pure iron, or is it a compound, like H2O? And if it's a mixture, is it homogeneous, all mixed up evenly, like salt and water, or is it heterogeneous, where you can see the different parts, like sand and water? See? A place for everything.
Okay, so we've got our building blocks. We know what matter is, but just having a pile of Legos doesn't mean you can build the Death Star, right? You need the instruction manual. And in chemistry, that's the rule book, the laws and measurements that make it all work.
To make sure everyone is on the same page, scientists everywhere use a standard system, the SI units. It's the universal language for measurement. We measure mass in kilograms, the amount of a substance in something called a mole, and length in meters. This way, a scientist in Brazil and a scientist in Japan are always speaking the same language.
And the very first rule in the chemistry rulebook, this is the big one, the law of conservation of mass. All it really says is this: you can't create or destroy matter, period. If you start a chemical reaction with 10 grams of stuff, you have to end with 10 grams of stuff. The pieces might be rearranged into something totally new, but nothing is ever lost. The universe doesn't lose its Lego bricks.
Okay, so we've got our blocks, we've got our rules. But this brings up a massive problem. How on earth do you measure your ingredients when they're individual atoms, things that are way too small to see?
Seriously, think about it. You can't just pick them up and count them one by one, right? How do you count something when there are trillions and trillions of them in even the tiniest little speck?
The answer is a brilliant shortcut, and it's one we use every day. You don't say, I'm going to the store to buy 12 eggs. You say, I'm buying a dozen eggs. Dozen is just a word that means 12. Well, chemists do the exact same thing. They use the word mole. A mole is just a word for a specific and very large number of particles.
And that number is this. Just look at it. That is Avogadro's number. We're talking 602 sextillion. It's a mind-bendingly huge number, which is exactly why chemists needed a shorthand. Instead of saying that whole number, they just say 1 mole. Simple. It's just the chemist's dozen.
So now we can count our invisible atoms using the mole. We've got our ingredients measured out. It's finally time to hit the chemical kitchen and start following some recipes.
Now, the fancy sciencey word for this is stoichiometry. Don't let it scare you. It literally just means chemical recipe. A balanced chemical equation tells you the exact ratio of ingredients you need. For example, to make water, the recipe says you need 2 parts hydrogen for every 1 part oxygen. That's it. Follow the recipe. But what happens when you don't have the perfect amounts? Just like when you're baking cookies and you run out of chocolate chips first?
In chemistry, that ingredient you run out of first is called the limiting reagent. It's the thing that limits how much final product you can possibly make.
And this sandwich analogy makes it perfectly clear. Let's say your recipe is 2 slices of bread plus 1 slice of cheese makes 1 sandwich. Okay, you've got 10 slices of bread, but you only have 3 slices of cheese. So how many sandwiches can you make? That's right, only 3. You run out of cheese, even with all that extra bread lying around. In this case, the cheese is your limiting reagent. It's in charge of the final count.
So let's recap. We've figured out our building blocks, we've learned the fundamental rules, and we know how to follow the recipes. We can go from single atoms to complex molecules. But, so what? Why does any of this actually matter in our everyday lives?
Well, because understanding these basic ideas is how we've built the entire modern world. Those life-saving cancer drugs like cisplatin and Taxol, that's pure stoichiometry, figuring out how to make the most of a reaction. The drugs that fight AIDS, like AZT, same thing. The amazing materials in our phones, the fertilizers that feed billions of people, all of it, every single thing comes from applying this fundamental rulebook.
And that's really the power of it all. With this simple rulebook, we've created medicines, we've built incredible technologies, and we've completely reshaped our planet. This knowledge literally built the world we live in. Which really only leaves one final and pretty exciting question, doesn't it? What are we going to build with it next?